Hello everybody, this is Mr. Zarzak, and welcome to the Glenbard West Physics Graphing Procedure Screencast Tutorial. So here's the data that we're going to be working with in graphing in this tutorial. Whenever we graph in physics, we're always doing it with a purpose, and that purpose is to try to discern or learn some new meaning from the data. Okay, it's all about interpretation. In this tutorial, I'm going to cover how to set up graph axes from given data, focus on how we approach finding the slope. I'll touch a little bit on slope interpretation. That's something that we're going to develop throughout the year and is a pretty darn important concept in physics. And finally, we'll focus on properly formatting the equation of the line. I'm sure you have plenty of experience with graphing from your math class, so I just wanted to show you this over here on the right side of the screen. This is data presented as ordered pairs, which is a very common practice in mathematics. Over here on the left side of the screen is our data table, and you'll notice that there is a correlation here. Okay, we present the information in a data table, and that corresponds to, well, your ordered pairs. If you're looking over here at the ordered pairs here for a second, okay, that first number presented in the ordered pair, so anything in this column, typically in math class would consider that your x variable, and the stuff in the right-hand column is considered your y variable. Okay, an important difference between math and physics, though, is that we're not going to be creating graphs of x's and y's. Okay, we're going to be creating graphs of data. In this case, our data is time and distance. Okay, so instead of an x-y graph, we have a time and distance graph. So let's get right into it. As you're watching this tutorial, I encourage you to pause it, go back and re-listen. All right, and you also might want to take some notes on the side as well. Our first step here is going to be to label our axes. Now, if you look at the data table, all right, the data is presented very nicely with column headings of time and distance, okay, and then units of seconds and meters are included. With the data presented this way, just like in math class, that first variable in the, or that left-hand column, okay, is going to be equivalent to what we're going to be plotting on the horizontal axis. And the stuff in the right-hand column is what's going to go on the vertical axis. So as far as the labels, all you need to do is transpose what you have in the column headings to the graph itself. And so you see here, distance on the vertical axis, and notice that I'm putting the abbreviated form of the unit afterward in parentheses, and time on the horizontal axis, again, the abbreviated version of the unit within parentheses. Now, any graph that you make in physics will need a title. When we title our graphs, we follow a format. Okay, the format that we're following is whatever we plot on the vertical axis versus whatever we put on the horizontal axis. So, because we've got a distance and time graph, the title of our graph literally is distance versus time. And you'll always want to follow this convention, okay? If a useful trick or a memory trick might be to remember that it's always y versus x, except instead of y, we've got to look at what we actually got on the vertical axis, which is distance, and instead of x, we've got to look at what we actually have on the horizontal axis, which in this case is time. If instead of distance on the vertical axis, say we had velocity, well, then the name of the graph would be velocity versus time, okay? Like I said, we always follow the same format. Now let's focus on setting up the axes. All right, when presenting information on a graph, you're presenting data in a pictorial form. The clearer you can make your picture, the better the chance that you or anybody else looking at your data will have at correctly interpreting what you were trying to communicate. Okay, so this graph grid is 20 by 20, which means that there's 20 boxes going up and down, and there's also 20 boxes going left to right. If you want to take a moment to count it for yourself, go right ahead. When scaling the graph, you've got to consider how much graph space that you have and also the range of your data. Okay, so I'm going to start by looking at the time data. And just scanning through the data, I can see that my time value, the minimum value is over here at 0. Okay, and very nicely this data goes in order, so my maximum is at 4. Okay, I know I have 20 boxes. All right, across the horizontal axis of my graph. That's how much space I have to work with. Okay. And the range of my data, to get that range, all you got to do is subtract your maximum value, which is 4 seconds, from your minimum value, which is 0 seconds. Okay, and this is useful to note because the graphs don't always start at 0, 0. All right, and so if I look at that, this reduces down to, let's see here, this would be 20 over 4. Okay, notice that I have these units here of boxes per second, and if I just take and I reduce that fraction, 20 divided by 4 tells me that for every 5 boxes, that's going to be equivalent to 1 second of time. So jumping back to my graph, okay, my first data point was at 0.00, so I'm going to start right over here in the lower left of my graph. Okay, and I'm just going to put the numerical value, and the way that I have this set up is I'm going to go and I'm going to skip 5 boxes for every 1 second. So if I look here, so this would be 1 box, 2 box, 3 box, 4 box, 5 box. Okay, and that's where I'm going to put my next little mark, and then I'm just going to repeat that process: 1 box, 2 box, 3 box, 4 box, 5 box, and that's where I'm going to put my next little mark and repeat the process again: 1, 2, 3, 4, 5, just like that. Okay, and last one: 1, 2, 3, 4, 5. Okay, and because I've got this set up the right way, when I go through and I make my labels, so this would be 1.00, 2.00, 3.00, and 4.00, just like that. If I peek back over to my actual data, okay, my data goes from 0 all the way up to 4, so I got my graph scaled really nice now. Now looking at the distance values, okay, I'm just going to do a quick skim through the data. Okay, and I do see here that, yes, the minimum value is at 0.00 and the maximum distance at 15.0. Do take a second to scan the data because the maximum value is by no means guaranteed to be the final value in the data table. Okay, in the graph itself, I have 20 boxes up and down to work with here. And again, to determine my range is just the difference of the maximum distance and the minimum distance. All right, and let's see here. So that gets me to 20 boxes, all right, for every 15 meters. Now, in reducing that down either to a fraction, 4/3 boxes per meter, okay, or if I want to represent this in a decimal, okay, if I put that in my calculator, you'd actually get 1.33 boxes per meter repeating. Okay, so that's not very nice, and the purpose of the graph is to make the data easy to interpret, and if I'm trying to do every 1 1/3 boxes, well, I'm making more work for myself than that's necessary. So what do I do with this 1.33 boxes per meter? Well, you're going to take it and you're going to round it, okay? And when you do this rounding, when it comes to graph axes, you always have to round down for that range, or else you're going to run out of graph, okay? So for the distance values, it actually turns out to be pretty simple. You just need 1 box for every meter. So looking back at my graph, every little line on a box represents 1.00 meters. Okay, so regardless of whether or not I choose to put a little tick mark on every one of these boxes, it's not necessary to label every single meter. It's going to get cluttered in there. So I think what I'm going to go through is plot. There's my 0. Okay, and I'm going to skip. The next one I'm going to throw on is 2.00 meters. The line represents 3 that comes after it, but then I want to skip up to the next, which is 4. Okay, I'm going to continue the process. And you can see here on this slide, I've just laid this out nicely to make it nice and neat. Okay, so now it's time to plot the data. All right, looking at my data table, my first value occurs at 0.00 and 0.00. So I'm going to go through, all right, and I'm going to zoom in here, and let's plot that little point. Okay, now that looks kind of dark, so what I'm going to do to make that more apparent, all right, is I'm actually going to put a circle around it, which kind of makes the point look like a donut, which I kind of like thinking about it that way because we say in physics that we plot donuts, not points, because they taste better. You could also think of this as a protector for your point. Okay, data is very important in physics, so you're putting that circle around it to protect it. But the reality is that you're doing that to make the data point as visible as possible, so that there's no confusion as to whether or not that's just a mark on the paper or that was done intentionally as a point. Okay, looking at the next. All right, I got time at 0.50 seconds, so halfway in between 0 and 1 here, and a distance of 1.70 meters. So this would be the 0. This line is the 1. That is the 2. So I'm somewhere in between the 1 and 2, a little bit closer than the 2. Okay, so I do need to make some of an estimate there, so I'm going to put my next point there and circle it and give it my point protector. All right, the next data point is at 1 and 3.5. So I'm going to find 1 on the time axis. Okay, and then there's 4, so this line down here, that's the 3. So halfway in between the 3 and the 4 line is where my next point is going to go. So right about there. Okay, and I'll circle that. And I'm going to continue the process of plotting the data, remembering to put that little extra circle around, or we say we plot the donut. Okay, so I finished plotting out my data on the graph, and hopefully you can see here already that there's something happening here. The distance is getting bigger as the time is getting bigger. All right, the graph is going up and to the right. To numerically interpret that data, we're going to draw a line of best fit. So this is something that you want to do with a ruler. And when you're doing your line of best fit, you want to move your ruler around a little bit to get it to, they call it a line of best fit literally because we're fitting a line as best to the data as possible. So I've done a little bit of adjusting here. Okay, and this line to me looks about as close as I'm going to be able to get it to fit the data. Notice that the line of best fit doesn't go through all the points. Okay, whenever you make measurements in the lab, there's always inherent measurement error, and that's okay. That's what we expect. The other thing I wanted to point out was that this graph looks like it goes through 0, 0, but the graph doesn't necessarily have to start at 0, 0. Okay, when you draw the line of best fit, you're taking that line and you're fitting it to the data that you have in front of you. You're making it fit that data as best you can. Next, we're going to calculate the slope of this line. In order to do that, all right, we need 2 points that occur on our best fit line. So I'm going to look at my best fit line, and I'm going to choose 2 new points. All right, in physics class, we ask that you pick points that are non-data points, so don't use any of the donuts. Pick 2 new points, okay, and label them in some way that is different from the donuts. So I'm just going to use this little red X here, all right, and then, let's see, let me find another one. Okay, it's okay that the best fit line crosses your graph axes in a nice convenient location. So I'm trying to pick spots where it looks like my best fit line kind of goes through an intersection on the grid. All right, but we want those points to be nice and spread out. Okay, you don't want to pick a point here and then try to find something over here. And the reason that we require that you pick points that are spread is that's going to minimize any measurement error that occurred when you drew that best fit line. Okay, so now on the graph, so that we can use them, we're going to take them and we're going to label those points right on the graph as an ordered pair, just like you would do in math class. Okay, so just looking at this first data point here, okay, it's on this line here right before the 1.00 on the time axis. So the question is, well, how much is that? All right. If you remember from when we scaled the graph, it's every 1, 2, 3, 4, 5 boxes is equivalent to 1 second. So to figure out how much each individual box is, okay, all we have to do is say, all right, well, we've got a second's worth of time that we've divided up into 5 boxes. All right, and if we take the number 1 and we divide it by 5, all right, that's going to give us a decimal value of 0.2 seconds for every 1 box. All right, so if I go and just count the boxes, okay, this value occurs on the 4th one, so I'm just going to count out loud. So this box here would be 0.2 seconds, 0.40 seconds, 0.60 seconds. This is 0.80 seconds. 0.80 seconds. All right, and then looking at the distance value, okay, that one hits right at the 3.00 meter mark. So I'm just going to label that right in the order pair, 3.00 meters. All right, and then I'm going to pop up here to this next data point. All right, and again, each one of the boxes is worth 0.2 seconds. So here's 3.00, which makes the next box 3.20. This would be 3.40. This would be 3.60. This would be 3.80, and then there's our 4. Okay, the time value occurs at that one right before the 4.00, so that's 3.80 seconds. So let's go and label that right on the graph itself. All right, and let's see here, the distance crosses right at 14.0 meters. Okay, that's a little sloppy, but I got a cleaner version a couple slides ahead. Ta-da! Alright, so now let's move into the slope calculation piece. Alright, you've probably heard the terms rise over run from math class, alright, or hopefully you've heard the term slope is equal to the change in y over the change in x. Okay, and when you see this triangle, okay, that's the Greek letter delta, and we use that Greek letter delta to signify a change. And you'll see that a lot in physics. And anytime you see that, that always tells you that you're going to subtract two values. Your final value from your initial value for y, so y2 minus y1, over your final value for x minus your initial value for x, or x2 minus x1. So now in physics, when we're doing our calculations, there's an important difference now from math class, and that's that, well, we're not making an x and y graph. All right, the data that we've plotted, all right, is data of distance in meters and time in seconds. All right, and what we're trying to do is discern meaning from that slope. So part of the way we do that, okay, is we use variables that will hopefully show us what some of that meaning is. So let me show you what I mean. All right, in the vertical axis of our graph, it's distance, which I'm going to abbreviate as d. So when we calculate the slope of this line, I'm actually taking the change in distance, all right, and I'm dividing that by the change in what we have on the horizontal axis, which is time, which I'm going to abbreviate that as t. So for this particular graph, all right, the slope value, which you should be familiar with that equation, is actually going to tell me a little something about average speed. Okay, and so I'm going to rewrite my equation, d2 minus d1 over t2 minus t1. When you're formatting your equations, this is what we want to get used to. Okay, we're going to want to say our goodbyes to x and y, all right, and get used to seeing those different variables. Variables are just unknowns. We're using those variables to try to learn something more. In physics, whenever we perform a calculation, we always start with the symbolic equation, okay, and this is our symbolic equation. Either of these is fine. You don't need to have both of these. In fact, I would prefer that you have this just because it's a shorter notation, and as time goes on, you'll be used to seeing that little triangle and saying, all right, we need to subtract now. So let's go through and perform the calculation. All right, looking at our data, our second data point, our second value for distance was 13.0 meters. Our initial point for distance was 3.00 meters. And I'm going to take and I'm going to divide that by the difference in our two time values. So our final time occurred at 3.60 seconds with our initial time at 0.80 seconds. Notice that I've written my symbolic equation. I've now substituted my values. I've kept the number of sig figs that's in my data. Okay, and notice that when I first set my values, I'm showing the units. Okay, that's going to be a useful self-check as moving along. 13.0 minus 3.00 meters, so I've got 10.0 meters. All right, over the difference between 3.6 and 0.80 seconds, so I've got, let's see, that would be 2.80 seconds. All right. When I evaluate 10.0 divided by 2.80 seconds in my calculator is going to return a non-repeating decimal of 3.571428.571. okay, which is way, way, way too many digits. All right, we don't want to record all of that because that's going to give somebody the impression that we had way more precision available to us than we did. So if I look at the number of significant figures in the calculation, 1, 2, 3 in the numerator, and 1, 2, 3 in the denominator, for addition and subtraction, it's always the number with the least number of significant figures that we're going to do our rounding to. They both have 3, so this becomes nice and easy for us. It's that third digit here, that third sig fig of 7, where we're going to look at this value and what comes next. All right, because this is where we're going to round. So the next digit is just 1. All right, so that works out really nicely. So I'm just going to round to 3.57. And do not forget your units. Okay, so that value right there, that's the slope of my line. And if I look at the equation that I used to calculate the slope, okay, hopefully you recognize this as our simple equation for average speed. You can also take a look at the units of meters per second. That's our standard unit for speed as well. All right, the slope tells us the speed of this object. In this case, it's a ball rolling along the floor. Now for the equation of the line. In physics, we're always going to use this slope-intercept form, which you're probably familiar with as y equals mx plus b. But again, this is not an x and y graph. All right, this is a distance and time graph where the slope tells us the speed. If we jump back to our graph, you can see that it looks like my best fit line really does go through 0, 0 here, so there is no y-intercept. There is no distance intercepted. Time is equal to 0, which just means that we started collecting data at some reference point. If we needed to calculate the y-intercept, we'd have to pick one of our points and go back and evaluate to solve, but we don't need to cover that for now. Taking a look at that general format here, okay, our y-intercept is 0, so we don't have to worry about that. Rather than writing x in our equation of the line, we're going to substitute in time. The slope is the actual speed that we calculated, all right, and our vertical variable is the distance. So looking at the way you'd present the equation of the line, there's our vertical variable d. There's our horizontal variable t. Here's the actual slope that we calculated, which represents the actual average speed of the ball. So I've got a numerical value with the units in the slope. I'm going to take that equation of the line, d equals 3.57 meters per second times t, and I'm going to write it right on the graph because, after all, it's the equation that describes this graph. And with that, we've come to the end of our tutorial. Thank you for watching. I encourage you to look back through the different parts of the tutorial that you feel you need to practice on. This has been Mr. Zarzak, and this tutorial has been a presentation of the Glenbard West Physics Department. Thanks for watching.